Now we get to the reason we started studying Laplace transforms. So far with the Laplace transform, we've only been able to solve differential equations that we could already solve by another method. But now we're not only going to be able to solve new equations, we're going to be able to solve equations that at a certain point don't even have a derivative. How can it be a differential equation? Isn't a solution to a differential equation a function that satisfies some relation for the derivative? Well, it will allow the derivative to not exist at certain points. It's kind of interesting. In order to solve these kind of problems that arise a lot in subjects like engineering, suppose we have, for instance, a unit step function, sometimes called the Heaviside unit step function. It's equal to 0 for t less than 0, and then at t equals 0, it jumps up to 1. So it's a unit, one unit step that it makes. Or more generally, maybe we want it to jump at some other time, like 1.5 here. Well, we'll just replace h of t with h of t minus 1.5. Right now, when t equals 1.5, this is equal to 0, it makes the unit jump down here. So replacing t by t minus t0, remember, just slides your function over t0 units in the t direction, and you can make the unit jump wherever you want by taking h of t minus some number. Alright, so this is the way an engineer prefers to draw it. We all know that it doesn't really instantaneously jump, but you model it that way with that function, and an engineer will draw this and it means that function up there. But the idea is really it just jumps up so suddenly and it's almost vertical and looks vertical. Alright, so now with this, we need another theorem to be able to handle it. Second shifting theorem. Alright, if t0 is bigger than or equal to 0 and the Laplace transform of little f of t, f of s, exists for real part of s greater than a, greater than or equal to 0, some number a, then for real part of s greater than a, the Laplace transform of the step function h at t minus t0, so it jumps over at t0, times f of t minus t0 is equal to e to the minus st0 times the Laplace transform f of s, of the original function f. Well, that's all real nice, except the way people use this in practice is backwards. They're given a transform that looks like this, and they'll say, well, what is the function that has this transform? If you see an e to the minus st0 multiplying a transform you recognize, you can realize you can undo it, go backwards, and find that the original function it came for was a shifted function, f that you knew shifted over times something that's 0 until t0. So that's what we'll say here. The reverse order is that if L inverse of f of s is equal to little f of t, and for real part of s greater than a greater than or equal to 0, then for real part of s greater than a greater than or equal to 0, the inverse transform of e to the minus st0 f of s is the Heaviside step function. It's equal to 0 for t less than t0, so you get the 0 function until t0, multiplied by this one shifted over to start at t0. So it works. Here's the proof if you want. Alright, the Laplace transform of the step function times f shifted is e to the minus st times that integrated from 0 to infinity. And then this can be broken up into two parts, right? Integrate from 0 to t0 and then from t0 to infinity, the same thing. But on 0 to t0, this function here is equal to 0, right? It's equal to 0 until t equals t0. So this is just integrating 0 is nothing. And you're just left with this one, the integral from t0 to infinity. And on this interval, h is equal to 1. So you make h equal to 1 here, just get e to the minus st f from t0 to infinity, and this one becomes 0. Now on t0 to infinity, you can now make a change of variables. Let t hat be t minus t0. That changes this integration to go from 0 to infinity and replaces t with adding this over t hat plus t0, and f of t minus t0 becomes f of t hat, and dt is equal to dt hat, right? You just take dt hat as derivative of this is 1 times dt. So this integral changes to this by the substitution method. But now what's this integral? Well, you can break e to the minus st t hat plus t0 into two pieces. E to the minus st hat times e to the minus st0, which can then be pulled out because this is a constant with respect to t hat. And now this is the Laplace transform f of s multiplying e to the minus st0. So there's a nice short proof that this actually works. Here's the kind of thing you might use this for in practice. You have some circuit or whatever, and initially you're putting 0 voltage in here until time t equals 1. Now you put a parabolic increase, and it looks like that. What is the equation for this function? If this is just the baby parabola y equals t squared shifted over 1 unit. Well, we know how to sketch that. Y equals t squared, replace t by t minus 1, moves the parabola over 1. So this is the graph of y equals t minus 1 squared, is y equals t squared shifted over 1 unit. Now if you multiply that by h of t minus 1, that multiplies it by 0 until t equals 1, and then starts that parabola. So I can get the right half of the parabola y equals t squared shifted over 1 unit by writing this function. How about that? This is part of the art, to be able to figure, what is this function that I tried to draw here? It's this one. Make it 0 out here with the step function, and then make it the parabola by shifting the usual equation. All right. So there's the graph, and there's the function. Now, what's its Laplace transform? By the theorem we just did, well, it's h of t minus 1, f of t minus 1, where f of t is t squared. So by the theorem, it's equal to e to the minus 1t, right? E to the minus, e to the minus 1s, right? Or 1 coming from here, whatever is subtracted, e to the minus 1s, times this function, with the Laplace transform of this function without the shift. So we take, what's the usual Laplace transform of t squared? Oh, we remember t over s cubed from the table, right? So e to the minus s, 2 over s cubed, is the Laplace transform of this very function we drew here. How about that? How about this one? The piecewise defined function. This is exactly what you need to be able to do functions that ramp or have corners in them, this kind of thing. What's the Laplace transform of this function, f of t? It's equal to 0 when t is less than 1. It's equal to 1 for t between 1 and 2. And then it's equal to 0 again for t greater than 2. It's a square function, right? It's 0 here, and then there's a little square here, if you like, and this one here. So there it is. We can write a description of that in terms of the step function, right? We can say it's equal to h of t minus 1. That will make it jump up at t equals 1, right? It would be 0 here and then 1 forever afterwards. But if we also subtract the function that jumps at a unit at t equals 2, we're subtracting, and we jump up to here at 1, and then we jump back down to 0 by subtracting 1 from t greater than or equal to 2. There it is. The description of this function is h of t minus 1 minus h of t minus 2. There's how you make a switch turn on and then off at particular times. So I take the Laplace transform of this strange function, this square function here, h of t minus 1 minus h of t minus 2. The Laplace transform of the difference is the difference of the transform, but we know this one. All right, what's the Laplace transform of h of t minus 1? I'm not multiplying anything this time. Yes, I am. I'm multiplying 1. This is, by the theorem we just did, e to the minus s times 1, since that's the shift, times the Laplace transform of 1, which was 1 over s. Right? Remember the Laplace transform of 1? And similarly here, this is h of t minus 2 times 1. So its transform is e to the minus 2s, since the shift is 2, times the Laplace transform of 1 is the 1 over s. So there's the Laplace transform of this square function. And we can do now differential equations that have these kind of things in them. Suppose, for instance, here's a very simple case. A second order equation, d squared u dt squared minus 9u is equal to a unit jump at t equals 2. Corresponding to some physical problem when there's a sudden unit forcing function applied at time t equals 2. We can put it together with these initial conditions, u of 0 equals 0, u prime of 0 equals 1. and transform both sides. Use our usual three-step method for recovering mathematicians here. Laplace, recovering people from the other methods we didn't like so much maybe. Laplace transform of the second derivative is s squared times the transform of u minus su minus u prime of 0. And then we'll subtract 9 times the Laplace transform of u, is u of s, we'll just change notation, equals Laplace transform of the step function we just found up here. The Laplace transform of h of t minus 2 is e to the minus 2s times the transform of 1 over s. This can be solved in the usual manner. Now we put in the initial conditions, 1 for this one and 0 for the other one. And then we solve by algebra. For u of s, we get s squared minus 9 multiplying u of s, and everything else we add over to the right, e to the minus 2s over s plus 1. And so u of s, the transform of the solution, is by dividing through by this, s plus e to the minus 2s over s times s squared minus 9. Alright. Now the solution is the inverse transform, right? This is the transform of the solution, so we inverse transform that. And what do we get? Well, remember when we see these kind of things, the trick is to factor the denominator. We can apply partial fractions to this eventually. First we'll say s over s times s squared minus 9 is 1 over s squared minus 9. And now e to the minus 2s has to be over the whole thing though. And when we go to take the inverse transform, we'll apply partial fractions to this part. It's 1 over 6 times s minus 3 minus 1 over 6 times s plus 3. That's the partial fractions decomposition of this. Similarly, 1 over s times s squared minus 9 has this partial fractions decomposition with 18ths and 9ths in it, and then e to the minus 2s can multiply everything. Now, what's the inverse transform of this one? I can pull the 1/6 out. To get it, and pull the minus 1/6 out of this one, pull the 1/18 out of here, pull all the constants out. Now I just need these transforms that I can find with our theorems and with the table. So the Laplace transform of 1 over s minus 3, we recall is e to the 3t. The Laplace transform 1 over s plus 3 is e to the minus 3t, inverse transform. How about this one though? You say, wait a minute, it's e to the minus 2s multiplying at something I know. 1 over s minus 3 was the transform of e to the 3t. When it's multiplied by e to the minus 2s, that means second shifting theorem, right? h of t minus negative 2, h of t minus 2 times 1/18 e to the 3t with t replaced by t minus 2. And over here, 1/18 e to the minus 2s makes that h of t minus 2 multiplying whatever is the inverse transform also shifted by 2. So s plus 3 is the transform of e to the minus 3t. I need to replace t with t minus 2 and multiply by h of t minus 2. So h of t minus 2 is this. And then 1 over s is the transform of 1, so I've got minus a 9th multiplying. 1 shifted is still 1. It just has to multiply the h of t minus 2. Alright, so there's the function. That's the solution of this problem. Well, if that's not hard enough, there's another thing we might do. Sometimes in lots of real-world situations, there's something that acts so fast that the velocity or momentum suddenly changes, right? It's not just the a unit step, but actually a jump in what we call an impulse, an instantaneous change in momentum. And in order to model that, we'll introduce what's called the Dirac delta function, named after the famous physicist Paul Dirac, did particle physics and so forth in the early 20th century, along with Einstein and all those other people. And delta of t is not really a function in this sense. There is a way to make it a function in an advanced setting, but not in this setting. Instead, what we'll say is the integral from a to b of delta of t minus t0 f of t, whatever delta of t means. This just means, when you write this by definition, it means limit as epsilon goes to 0 of the integral from a to b, the same integration limits, dE of t minus t0 f of t dt, and dE is actually a function. It's a rectangular function. It looks like this. I should call that d epsilon. Actually, I wrote epsilon. D epsilon is the function that's equal to 0 for t less than 0. It's equal to 1 over epsilon for t between 0 and epsilon, and then at epsilon it goes back to 0. So it's got a rectangular area under here, and since it's 1 over epsilon high and epsilon wide, it's a unit area function. It's equal to 0 except for this unit area between 0 and epsilon that it hovers over here. So that'll be d epsilon. It has this definition. And now, if I want to really think about it, this is a whole family of functions, right? It's an infinite number of functions, one for each epsilon greater than 0. Right? And for each epsilon, there's a function that's equal to 1 over epsilon, and then 0 again. And so here's the d epsilon function with epsilon equal to epsilon 1. Here's the d epsilon function with epsilon equal to epsilon 2, epsilon 3. You know, if we keep making epsilon smaller and smaller, these rectangles get higher and higher in order to maintain unit area. And in the limit, we get sort of an infinite spike here. Not really a function, but we're thinking of the Dirac delta function as the limit of those, because after all, when we put it in an integral, we take the limit of the integral with the rectangles getting narrower and narrower and narrow, heading towards 0. What's the limit as the rectangle width heads to 0, but it's still unit area? That's what this definition is. The Dirac delta function, when you see it in here, inside an integral, means the limit of the integral of this well-defined function, d epsilon. All right, so what is the Laplace transform then of the Dirac delta function of t minus t0? You could put this besides at 0 if you put delta of t. That was delta of t we drew, right? This is delta t. These come closer and closer to 0, but we can put it out here and put the rectangles out at some other point t0. What's the Laplace transform as the rectangles get narrower and narrower in their integral? Out here at some point t0, well, we'll say that the Laplace transform of delta at t minus t0 is e to the minus st0. Why should that be? Here's the proof. You just take the Laplace transform is the limit of e to the minus st d epsilon t minus t0 dt. That'll be the Laplace transform of the Dirac delta function. It's the limit as epsilon goes to 0 of, well, this function is equal to 0 unless t is between t0 and t0 plus epsilon, right? This is the shifted over function. And so I just integrate from t0 to t0 plus epsilon, because otherwise the integrand is 0. I'm not getting any area under the curve, if you like. And then d epsilon is equal to 1 over epsilon when it's between these values. So I have e to the minus st times 1 over epsilon when you're between those two values, and otherwise I'm just getting 0. And so this is limit epsilon goes to 0, and here's the antiderivative of that integrand. It's an easy thing to integrate, and we just need to plug in the top endpoint and the bottom endpoint, take the difference. That's what we get when we plug in the top and bottom and take the difference. And then there's a little trick here. This is kind of the tricky step. You factor in e to the minus st0 out of the numerator, and then say, well, wait a minute, there's no epsilon in here. I can pull it outside the limit. I guess I didn't bother to do that here. You can pull it outside since there's no epsilon in it. And then you have e to the minus s epsilon minus 1 over minus s epsilon. Limit as epsilon goes to 0. What's that come out to? Well, you could write the power series, right? This one is equal to 1, right? Power series for e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Or we'll replace x with minus s epsilon. So I have 1 minus s epsilon plus s epsilon squared over 2 factorial plus so on and so forth. So I put order epsilon squared here. There's epsilon squared terms of bigger in the remaining terms of the power series. All minus 1. And now, the 1 and the minus 1 cancel, and what you get is minus s epsilon over minus s epsilon, plus smaller terms with an quotient to minus epsilon 0, the limit goes to 0. So you can ignore these because their limit over s epsilon is 0. And what you have is 1 e to the minus st0 times 1 in the limit. And there is how you derive the Laplace transform of the Dirac-Delta function. So I'll put that over in this differential equation. Here's a differential equation where I impart a unit Dirac-Delta function times 2 in this case. Suppose I want to solve that together with these initial conditions. U of 0 is 1, U prime of 0 is 0, U dot of 0 is 0. We take the transform of both sides, but now the transform of the right is 2e to the minus s by what we just said. The Laplace transform of e to the t minus t0 is e to the minus st0. And Laplace transform of second derivative is, I put a couple steps in here, is s squared u of s minus s u of 0, which is 1, so that's where the minus s comes in here. And then minus Laplace transform of u is minus 1 u of s. So this is a quick transform of this on the left. You solve for u of s by dividing through by s squared minus 1, and you get this. And then you break it up into two pieces. Well, you know, we can do the methods we've been doing, but I want to point out that we're coming up now on a table. And the table has some of these things built in. If I want to take the inverse transform of s over s squared minus 1, how do I do that so far? I use partial fractions, and I break this into two pieces, and I can find out exactly what that is. It's got something times e to the t plus something times e to the minus t, it turns out. But once that's been done a bunch of times, you just make a theorem out of that, and you say, if I were to inverse transform this, what I would actually get is e to the t plus e to the minus t over 2. That's what I get out of this using partial fractions. But that's just a hyperbolic cosine. So you can memorize this one, that the inverse the transform of cosh is s over s squared minus 1. Similarly, the transform of 1 over s squared minus 1 is sinh. And so when I recognize, I can pull the 2 out. This is the transform of sinh. What's the inverse transform when I have e to the minus s? Remember the second shifting theorem. E to the minus t0s is the times the transform of a function I recognize is h of t minus t0 times that function evaluated at t minus t0. So if I had just 2 over s squared minus 1, I'd say, oh, that's the transform of 2 sinh. But if it also multiplies e to the minus s, I have to replace t with t minus 1 and multiply by h of t minus 1 by the second shifting theorem. So say there's the transform of twice sinh, e to the minus s, shifts it and multiplies by h of t minus 1. Look at what happened here. This is kind of interesting, actually. This is a problem that has a nice solution with a corner in it, right? When you add these two together, you get cosh for a while because this is equal to 0 until t equals 1, right? Because it's multiplied by 0 here. And then at t equals 1, you suddenly have this other function that's equal to 0 at t equals 1, right? Since if t minus 1, since if 1 minus 1 is 0, but it's got a certain slope that adds on, and so the sum of these functions is still continuous, but it has a corner in it. And it's like you turn on a switch in your circuit suddenly, and it went like that. So there's the solution of this differential equation has a point where the derivative doesn't exist. Because you did something, you inserted a unit impulse. Again, if this is a physical problem, you might consider, there we go, that you've got a billiard ball or something, and all of a sudden you hit it with the cue stick, and it instantaneously gets velocity. So if this is the position along here, all of a sudden your position doesn't jump, but your velocity does. There's a sudden jump in velocity at this point. It's that kind of a problem. Here, for instance, is an actual physical problem. Suppose you have a mass spring system and you want to find the displacement, U of t, right? U of t is the vertical displacement with positive downward. If you were to have a 2 kilogram mass on a Hooke's law spring with constant 8 newtons per meter, you could write down the equation for that. It's md squared dt squared plus ku equals 0 if there's no force applied. But now suppose you want to have a forcing function, a driving function if you like. And this driving function is initially equal to 0. You just let the spring hang there. And we'll say your initial conditions are 0. So suppose it's in equilibrium. Initial position 0, 0 velocity, so it's just hanging at the end of the spring. And now at time t equals 1, you instantaneously set a weight on it. I'm sorry, not instant, I instantly strike it. So I give it a 2-unit impulse at t equals 1. What happens to this thing? Well, it's 2 times delta t minus 1, and with the initial conditions. And what it does is it starts out hanging in equilibrium for a second because that's where it was hanging. You haven't done anything yet. Until t equals 1, all of a sudden you strike it. What does it do? Well, this is what it predicts. You take the transform of both sides and you get this. Right, here's the differential equation. I'll divide it through by 2 just to make it a little easier here. And the transform of the second derivative is s squared u of s minus 0 times s minus 0. And the transform of 4u is 4u of s, and the transform of the Dirac delta function is e to the minus s. We said a Dirac delta function at t equals 1 is e to the minus 1 s. T minus 1 is e to the minus 1 s. You solve this for u of s, you get e to the minus s times 1 over s squared plus 4. This looks familiar, right? 1 over s squared. So I wind up with h of t minus 1, 1/2 sine of 2t minus 1. The final result is correct. I just left off my 2 here and here. Here's what the answer looks like. The position is vertical. The time is on the horizontal, and initially the mass just sits there in equilibrium at t equals 1. I give it a unit impulse, a 2-unit impulse. And what happens then is that it starts oscillating sinusoidally because it's undamped mass in a spring. You just struck it and it starts moving in its usual